Okay, so I've posted this PDF. In the beginning here, this is just a reminder of rules of exponents. Particular focus on these two. I think that because a negative exponent becomes a fraction and a fractional exponent becomes a root, I think that's why people get it confused, but that's the most common thing for people to forget. So this is just kind of a review of exponents and logs. It's an extensive one, but use it as you need it, I suppose. Okay, so the first thing we're going to look at is exponential functions are of the form something to the x. So the variable is in the exponent, and so the reason that b has to be positive is because if b was 0, it would be just 0. No matter what x you take it to, it's always 0. If b was negative, then some powers would not exist. So like the power 1/2, for example, because that's a square root, would not exist. And some would be negative if you took a negative number to an odd power, for example, that's negative. If you took it to an even power, it would be positive. So basically, you'd have this crazy graph with stuff everywhere, above and below the axis, not connected at all, and also full of holes. So we just limit it to things that end up smooth and reasonable. And the reason it can't be 1 is because that would just be the constant 1. 1 to the anything is 1, so it would not be interesting at all. Okay, so we're going to graph this one. I guess I'll grab all of that even though it's going to get in my way. Okay, so if I take 2 to the negative 3, I get 1 over 2 to the 3. That's the one that one of the two that people tend to forget, is that a negative puts it in the denominator. So this is 1/8. Similarly, this one will be 1/4. One-half. Anything to the 0 is 1. So you're always going to get the 0, 1 point. 2 to the 1 is 2. 2 squared. 2 cubed. Okay, so I have 0, 1. I've got negative 3, 1/8. I don't think I can get all the way down to 1/8, but I'll try to get close. 1/4, 1/2. Over here, okay, so 1 goes to 2, 2, 4, 3, 8. And if I just connect these with a smooth curve, then you can see it's shooting off pretty fast that way and going towards 0 this way. This is when someone says something's increasing exponentially, it should mean this. It doesn't mean like to an exponent of 3. It means that the variable, usually time, is actually in the exponent. So it's growing very, very fast and faster all the time. So there's 2 to the x. So the domain of that was all real numbers. I can take 2 to any power I want, and remember, it looks like this. So the domain is all real numbers. The range is what the y's can be. And if you look at this, the y's are always positive. The reason is because 2 is positive. So whatever power you take it to, it continues to be positive. But if I take it to a really, really, really negative power, it's going to be really, really, really small. So it's going close to 0 over there. So the range is 0 to infinity, not including 0. So the domain is all reals. The range is 0 to infinity. Okay, the x-intercept does not exist because an x-intercept is when y is 0, and we can see here y is never 0. The range ends at 0 without including it, so there's no x-intercept. The y-intercept is 0, 1. Vertical asymptote does not exist. This looks like it may be, but remember our domain is all real numbers. This actually does keep going to the right forever. It just goes up faster than it goes to the right, but it doesn't approach an asymptote. There is a horizontal asymptote. The horizontal asymptote is at 0, and it only approaches it on one side. Oops. Okay. If I was going to graph 1/4 to the x, so I should have made these match. I should have made these 2.5, but I'm going to make this 1/2. So on your paper, you'll just change it to 1/2. Just take that part with me this time. Okay, so there's that. So my y values now, if I take, you can do a little note over here. 1/2, good grief, stop. 1/2 to the -3, that's so annoying, to the -3 is 1/1/2 to the 3. You know what, I'm just going to use this whole sheet to do this and then I'll erase it, because this is very annoying. Okay, 1/2 to the -3 is 1/1/2 to the 3, so that's 1/1/2 cubed. It's really 1 cubed over 2 cubed. If I invert and multiply, so I get 2 cubed. So really, if you have a over v, I may have put this on the rules. Well, actually, I stole those rules, so they may be on there or not. But anyway, ab to the negative something, a over b to the negative something, is b over a to the positive 1. So you can just flip it instead of going through this process and save some time. So when you see 1/2 to the -3, that's 2 cubed. 1/2 to the -2, 2 squared, okay? So just to save chalkboard space, I'm going to go ahead and say, okay, so that's 2 cubed, 2 squared, 2 to the 1. Anything to the 0 is 1, that includes fractions, so that's still 1. 1/2 to the 1 is 1/2. 1/2 squared, 1/2 times 1/2 is 1/4. Cubed, 1/2 times 1/2 times 1/2 is 1/8. Okay, so this time when I go to the -3 is when I go all the way up to 8 instead of at 3. -2 goes to 4. -1, 2, 0, 1, 1/2, 4, 8. That should not have gone up. Okay. Well, pretend that I did that correctly. So the domain is still all reals. The range is still 0 to infinity. The y-intercept is still 0, 1. The x-intercept still does not exist. There's still a horizontal asymptote at 0, and there's still no vertical asymptote. So all of that looks the same. So we want to consider what's different between when it's a whole number and when it's a fraction. And this is it. If you have a fraction, so you're between 0 and 1, it is decreasing. And if you're bigger than 1, your base, then it's increasing. Because here, you're multiplying by something bigger than 1 as you go to the right, so you're getting bigger. Here, you're multiplying forever by something less than 1 as you go to the right, so it's going to get smaller. But they're actually kind of mirrors of each other. So if I accurately drew 2 to the x and 1/2 to the x, that actually just mirror each other exactly. Okay, so this is a note that as you let n go to infinity, and you take 1 plus 1 over n to the n, you get e. That's why E has a name, because it's this. If you do this in a calculator, you'll begin to see that this is approaching this value as you just choose larger and larger and larger n. Compound interest formula. This probably is also a reminder, but let me go talk about it. Okay, so we're going to say that we have $1,000 to invest. And we're going to say that we're earning 6% interest. And first, let's just say that this just compounds once a year. So just every year I gain my 6% interest. So 6% interest of 1,000 is 60. So I should get 1,060 at the end of the year. But the way we get that is that we have our 1,000 and we add to that 6% of 1,000. So we get 1,000 times 1 plus 6%. Okay? And if I were to do this again, so I leave it for another year, I would take my 1,060 plus my 6% of my 1,060. So that would be 1,060 times 1 plus 0.06. But this itself was 1,000 times 1 plus 0.06. So now I've taken all that and multiplied by 1.06, 1 plus 0.06. And if I let it sit another year, then I'd take everything I had and I'd multiply it by 1 plus 0.06, and so forth. So 1 year, 2 years, 3 years. The 1.06 is happening every single year because every time I compound it, I multiply by that again. So it's 1,000 times 1 plus 0.06 to however many years. So T generally represents time in years. So this is how you would calculate the interest if it's just compounded once a year. This we call P, this we call R, and T again is time in years. Okay, so let me erase part of this. So I'm going to leave that bit. And let's say that we're going to leave this let's say we're going to leave it 5 years. So I would have 1,000 times 1.06 to the, I said 5, I think. So we would have 1338.23 at the end of that. So this is compounding annually. Okay? So now we're going to compound it instead, say quarterly. So what that means is that at the end of every 3 months, we do the compounding. So I don't get 6% per 3 months, I get 6% per year. So I would only actually get a quarter of this percentage. I wouldn't get $60, I'd get 15. Okay, so I get my 1,000 plus 1/4 of 6% of 1,000. So if I factor out the 1,000 this time, I get 1 plus 1/4 of 6%. So I'll just write 0.06 over 4. We could do that in our head and say it's 0.15, but we're trying to build up a formula, so it's better to kind of leave things this way. But the thing is that now I'm going to compound 4 times per year. So it's not going to just multiply by this once. I'm going to multiply by it at the end of March. I'm going to multiply by it at the end of June. I'm going to multiply by it at the end of September, and then at the end of December. So I'm going to do it 4 times every year. So if I have the time in years, and I multiply by 4, that's how many times I compounded total. Okay? So now, this is still P, this is still R, but these 4's are both N. And N stands for the number of times per year that you compound. So then when you multiply that by T, you have the number of times you compounded all together. Okay? So if we do this for 5 years, now I've got 1,000 times 1.015, because I did in this one time just do that in my head there. And now for 5 years, I've done 20 times. So I have an extra $8.50. Okay, so $13.46.86. Okay, so now I'm going to instead compound monthly. So that means that I get 1/12 of 6% of 1,000. So that's just 0.5%, but again, let's try to build a formula here. So we have 1 plus 0.06 over 12. And this time it's going to be to the 12t, because now I'm going to multiply 12 times per year. So I have the power of 12 times the number of years. So for this, I would get 1,000. So that didn't make too much of a difference there, just a couple dollars. Okay, so the exponential that comes up in the continuously compounding is because of this. Well, so from here we can see that I've taken the principal, 1 plus the rate over the number of compounding periods to the n times t. This is equal to p times 1 plus r over n to the n to the t. Right? That's just a rule of exponents that we just went over. So I want to look first at this. So there's another thing that I didn't say on the previous page. Let me not use the word limit here. So as n goes to infinity, 1 plus x over n to the n goes to e to the x. So this was that 1 plus 1 over n to the n went to e as n goes to infinity, but actually this is also true. So you can see how this looks like that. So that means that as n goes to infinity, and n, remember, was the number of compounding periods per year. So if we want to talk about something continuously compounding, we want to let the number of compounding periods go to infinity. That should equal e to the r. So now we have p e to the r to the t. This is as n goes to infinity, right? So as we go to continuously compounding, so this is p to the rt, again, just a rule of exponents to bring that t out. That's where these formulas come from, and that's the reason E does this, is because E is just what we named the guy who does this thing. So if we did this now, continuously, 1,000 times E to the 0.06. Oops. Oh, I guess I have to do it with the button over here. Okay, so 1000 e, it's a little bolder, to the 0.06. Okay, 1061.80, that can't be right. Oh, I forgot the 5. So this is to the RT, so 1000 e to the 0.06 times 5, 1349.86. So this is continuously. We could have also done daily. Now, generally speaking, in most textbooks, they consider there to be 30 days in a month, every month. Okay, I was interrupted, so I may repeat myself here. But generally, in most books, they consider a month to be 30 days, even though there are certainly not all. They consider, therefore, there to be 360 days in a year. So when they calculate a daily value, they do 360. But let me show you that it doesn't really matter, because while you're compounding 5 fewer times, you're getting a little bit better interest rate because you're dividing by a little less. So let's take our 1000 and not hit the wrong button. So 1 plus 0.06 divided by 365. Even let's do 0.25. Let's do the very exact number of days. So that's doing it accurately daily. And let's say that we do it for 5 years. So to the power of 365.25 times 5. And then let's do it with 360. See, somewhere in some decimal, it was different. And if you were doing this on a even TI-84, maybe even an Inspire if you have it in your hand, but then you would see a difference somewhere down the line. But you can see that when we rounded to a penny, it's actually the same. So it's so small a difference that it's fine to do for daily. So daily is 1349.83. And it's so close to being continuously that you only get 3 more cents from the continuously compounding. Okay, so because I've done this example, I may skip some of the other examples and let you do those and let you, come back to this and make sure that you're doing it correctly by reference. Okay, so let's see where I am here. So basically, I just did this. I did this for 1,000 and for 6%. So you do this and use the video as a guide. Okay, so logarithmic functions are the inverses of exponential functions. So if you have b to the y equals x, y is the exponent, y is the log is the exponent. Okay, so logs are exponents. So if you look at this and say, to what power would I have to take b to get x? That's log sub b of x. The bases will match. It's called a base in both cases. So to just change them back and forth, log sub 6 of x is 2. So 2 is the exponent because the log is the exponent. 6 is the base. So base to the exponent equals the argument of the log. And that's done. For b, so 3 is the exponent because the log is the exponent. The base is x. And the argument is m. So we can't write this as a number because we have 2 variables, so we don't know, but This is writing this guy in exponential form. Okay? Now we're going to do the opposite thing. Okay, so log, the base is the base, so the base is 5. The log is the exponent, so the x goes over there, and the 10 is the argument. I think that remembering which thing is the argument is the hardest. So if you write down the log is the exponent and the base is the base, and then just the spot that's left over, you fill in with whatever's left over. Okay, so the base is the base, the log is the exponent, like that. Okay, so now we're going to use this to solve these. And most of you can put this in your calculator actually, but we didn't have calculators that did different bases without doing a change of base until quite recently. So it's better anyway to do it this way to understand. So log sub 3 of 27. So we'll say x, y, tree, your name, a rainbow, whatever, just name it. If you name it, then you can use the formula, the equivalent formula. So the base is the base, the log is the exponent. So 3 to the what is 27? And you can just count that out if you want. 3, 9, 27, done, 3. Okay? This one's a little bit different because now we have this 1/8 instead of 8. So if I name it y, then we have the base is the base, the log is the exponent. This is 1 over 2 cubed, right? But using the rules of exponents, we can write that as 2 to the negative 3. And now we can see 2 to the y is 2 to the negative 3. At any point that you want to pause, it makes sense if I'm about to do an example to pause, do the example, and then I'll do it and you'll see if you got it right. Okay, so this one has a name because we have 10 fingers, so our number system is base 10. This one has a name because it shows up everywhere in nature. So the common log is just log like that in your calculator. Log base E, natural log, is ln. Okay. So anything to the 0 is 1. Therefore, if 1 is your argument, no matter what your base is, the exponent is 0, and the log is the exponent. B to the 1 is always itself. So if it's just the same number, log sub 2 of 2, log sub 5 of 5, natural log of E, that's always just going to be 1, because that's the power you take it to get itself. Because they're inverses, b to the log sub b of x is x, and log sub b of b to the x is also x. Okay. So if I rewrite log sub b of x, I'm going to say this is b to the y, where y is log sub b of x. That means in exponential form, the base is the base, the log is the exponent. So b to the y equals x, but this was y, so b to this equals x. So that's this one. Log sub b of b to the x, we'll call that y now. Then that means the base is the base, the log is the exponent. So y equals x, so this equals x. Those are quick proof, but a proof, if you play it over and think about it, it'll be hopefully clear. Okay, so 5 to the log sub 5 of x, x. Log sub anybody of 1, 0. Log sub 6 of 6 squared, 2. The log sub 6 of 6 cancels. Natural log is log base e. So natural log of e to the 10, 10. Natural log of e, 1. Because remember, if it's the base and the argument are the same, it's 1. E to the natural log of x, x. Log, since it's base 10 of 10, that's 1. B, that's random, sorry. I'm not sure anymore that I want to do this, just for the sake of time here. But each of these gets reversed over here because they're inverses. So negative 3 1/8 means 1/8 negative 3. Negative 2 a fourth, negative 2. Well, negative 1 1/2, negative 1. You know what? I'm going to do this very, very, very quickly, okay? So these are all reversed, which means instead of negative 3 1/8, I go 1/8, negative 3. Instead of negative 2 a fourth, I go a fourth, negative 2. Negative 1/2, 1/2, negative 1. 0 1, 1 0. 1 2, 2 1. 2 4, 4 2. 3 8, 8 3. So you'll see that this is just like the exponential function if you flipped it and then flipped it again. If you turn your head to the right, then it'll be the reverse of the exponential function, but of course if you turn your head to the right, y positive is to your left and negative is to your right, so it would be flipped. So it's basically the opposite graph here, which is what happens when you have inverses, of 2 to the x. Which means these are all opposite. The domain is now the positives and the range is the reals. The x-intercept is 1 0 and the y-intercept is the guy that doesn't exist. The vertical asymptote is at 0, x equals 0, and there's no horizontal asymptote because everything's reversed. So I just said that. Okay, so the inverse of 2 to the x is log sub 2 of x. The inverse of log sub 9 of x, 9 to the x. Okay, so the domain, because remember its domain was all positives, then even if you have some other mess inside here, that thing has to be positive. This says functions because I originally had more, but this is already going to be a crazy long video, so I'm just going to do this one. Okay, so log sub 3 of 2x plus 1. So all I have to do is whatever's in the parentheses, that needs to be positive. And then I just solve algebraically. And that's it. So that's the domain. Okay, so I'm going to make kind of a little proof for one of these and then a kind of hand-waving proof for the other two. So basically it comes down to this. If you consider, let's say that we're doing log sub A of m times n. Okay, so we're trying to get it in terms of log sub A of m and log sub A of n. So I'm going to just replace these. M can be written as A to the log sub A of m. N can be written as A to the log sub A of n. That's just using the facts we just now learned. If I do A to the log sub A of, those cancel, right? Using the rules of exponents, I can now then say that's A to the log sub A of m plus log sub A of n, right? And then I'll assume you said right. So now I've got log sub A of A to the something, and the something's a mess, but it doesn't matter. These cancel each other. Log sub A of A to the is whatever is after the word the. So this is equal to log sub A of m plus log sub A of n. So log sub A of the product is log sub A of one plus log sub A of other. And it's because a log is an exponent, and if you do a product, you add the exponents. So if you do a quotient, like A to the m over A to the n, you subtract. This is log sub A of m minus log sub A of n. And because if you do a power, you multiply. If I do log sub A of m to the n, I multiply. And the argument for these is similar to the argument of the first one, but this one is extremely helpful because this means I can get things out of exponents. And without logs, you can't really solve for values in exponents because they're stuck. But once you start dealing with a function which is an exponent, then you get to pull it down. So these are the properties. So we're first just going to practice using the properties. I guess I'll get two of these at a time. So you look at the first one, and you see inside here a product. So this is log sub 4 of 2 plus log sub 4 of x. This one, because 4 to the 1/2 is 2, I could replace. Okay, so if I can say I'm going to take this to some power and it will yield that, then the log is doable here. So this one I would simplify like that. This one, because that's a quotient, and quotient subtract. This is a number, but there's no better way to write this number than natural log 3, so we'll just leave that one. Again, you can try these first, pause, and then come back and see. Okay, so this one, the first thing is that there's a product. So log sub 8 x squared plus log sub 8 y cubed. but I still have exponents, so I'm really not done. So I bring down the 2, bring down the 3. This one, I first have a quotient, so natural log 3x to the 5th minus natural log y squared. I still have a product here, and since the 3 isn't to the 5th, I can't bring down that 5 yet, so natural log 3 plus natural log x to the 5th minus, bring down that 2. I still have that 5 to bring down. And then there's nothing else. There are no more powers, exponent. That's the same. Powers, products, or quotients. Okay, so this is doing the reverse. I think I won't do all of these. There's quite a bit still left to do, and this is a pretty long video right now. I'm going to do... I'll do this one. Okay, so the first thing is I can't combine these as long as they have numbers on the outside. It has to be just log blah plus or minus log blah plus or minus log blah. So I've got to get those out first. So natural log x cubed, natural log y to the 4th, natural log z to the 6th, like that. And then I can combine these first. You really can do them all at once, but in case that might mess you up, let's just do 2 at a time. Doing the plus is easier than the minus, so let's do that first. So that would be a product. If the exponents are being added, then you started with a product. And now the exponents are being subtracted, so you had a quotient. Okay. So to solve, how many examples do I have? 3. Okay. So to solve using natural logs, I'll do, I guess I'll do them all, but you try them too. So we have this, isolate the exponential expression, then take the log, then simplify and solve. Okay, so these are already isolated. The exponential expression is the b to the x. So it means don't have like 12 b to the x, don't have b to the x minus 8, just b to the x, or x plus 1, because that's in the exponent, that's fine. Okay, then I take logs of both sides. Then I bring down the x. I don't do anything over here because this is just exactly equal right here. But then I've got x times a number is a number, and if this said 2x equals 3, you'd be perfectly happy with me dividing by 2, right? So let me do this. For this one time, let me call this moon and star. So I have x times moon equals star, and moon is natural log 5 and star is natural log 10. So then if it looks like this, I think everybody's okay doing this. So now we've solved for x. So that's natural log 10 divided by natural log 5. So you can substitute for things, column A and B for all I care, but you can substitute if it helps you at first to not be bothered but people tend to treat these like variables, and they're not. They're just numbers. They're irrational generally, but they're numbers anyway. Okay, so for this one, again, the exponential expression is already isolated. So I can take natural logs on both sides, bring this down. So I've got x plus 1 times something equals something else. So I need to distribute. Natural log 3 times x plus natural log 3 is natural log 7. These are all just numbers, so I'm just going to subtract that one. And then I'm just going to divide by the number next to x. Okay? And then you just put that in your calculator, and it's a mess. But if you're, well, you may put it in the calculator depending on how you're asked for the result. Okay. This also has the exponential expression already isolated. This time, I don't even really have to bring it down because I have natural log of e to the something, so that's just the something. I could bring it down, and then I'd have x plus 5 times natural log e, but natural log e is 1, so it would still disappear. So I just subtract 5. And that's that. Okay. I don't think I'll do all of these. Let me do the last two, maybe. And again, feel free to pause, give it a go yourself. Okay, so what we're going to do is the rules are convert it to exponential form and then solve. Go. Okay. So first I have to have natural log of something, not with this 6. So natural log, oh, actually, I can just divide, so I would bring the 6 up, which you can do, but then you'll have 2x to the 6th, and so you'll have a 2 to the 6th. You could also notice that 6 and 30, 6 divides into 30, so you could change this. Just dividing by 6 on both sides. So our base is e, the log is the exponent, there's the argument. I'm trying to solve for x. So there's x, e to the 5th over 2. Okay, so this one, 6 to the 5x plus 3, because I don't have a number out here, so I can just jump right in. 6 to the 5x plus 3, the log is the exponent, the base is the base, is 36. But 36 is 6 squared. So now I can just say 5x plus 3 is 2. 5x is negative 1, subtracting 3 on both sides. X is negative 1/5. So try A and B. Okay, so logarithms and exponential functions are 1-to-1, which means if you have that log sub b of one thing is log sub b of another thing, then they're actually the same. So log sub 5 of 2x minus 4 equals log sub 5 of 10 means 2x minus 4 is 10. So you can do that yourself, starting with 2x minus 4 is 10, I think. And here, So on this one, you just say 5x minus 2 is 3x plus 7 and solve. So let me just look at this one, because this one's the only one that has any different step. So the first thing is it has to say log sub 6 of something is log sub 6 of something. You can't have this. So we have to first get this into a single log. And because this is times, that means it was raised to a power. So I bring the 3 up. Now I can say 5 cubed is x. Nope. Okay, so now we're coming back to this, and I think hopefully, well, eventually we'll get finished. So what interest rate would be necessary to grow $5,000 to $9,000 if the interest is compounded monthly for 4 years? So let's just write that all down. We have A equals P 1 plus R over N to the NT. So we have A, we have P, we don't have R, monthly, so N is 12, okay, so first I would divide by 5,000. 9,000 over 5,000 should be 1.8. Now, for this, I need to get rid of the 48 to get to this R. So I need to take this whole thing to the 1 over 48. Of course, anything I do on one side. So 1.8, 48, the root, is 1 plus R over 12. Subtract 1, multiply by 12, that equals R. Okay, so 14.785%. That's very huge, but you think about it, to almost double your money in 4 years, you'd have to have a pretty serious rate. Okay, how long would it take your investment to double if your account earns 6% compounded continuously? Okay, so it doesn't really matter what the investment is to ask this question. So it's compounded continuously, so we have A equals P ERT. Okay, so if A is twice your principal, if you divide out the principal, you're just going to get 2 on that side. If you're going to triple it, you'll have 3. If you're going to half it, you'll have half. So 2 equals e to the 0.06t. Because I want this t out of there, I need to have logs. So I'm going to take a log on both sides. And so that cancels. So then natural log 2 divided by 0.06. understand what's happening. Okay, so it'd take 11 and a half years, which is a more reasonable amount of time to take to double. Okay, I took a little tiny break there, but so exponential growth, you'll notice, looks exactly like the continuously compounding formula, because basically if a population is growing exponentially, it's approximated by continuously compounding. So this happens where anything's growing, so growth of population. And if something is instead declining, then this is exactly the same too, except we put negative k, and that really just mostly indicates that your exponent's a negative number. So if it's decreasing, then k is going to be negative. So this is the amount that's there after t time units. It could be in seconds, minutes. On the interest formula, it's always years. On the exponential growth and decay, it varies, but it's specified in the question. A sub 0, it's called a naught really in a UGHT, as in nothing. But it's not that you had nothing. It's before any time passed. So a naught is what did you have when you first started counting. And then k is the growth or decay rate. Half-life, which you've heard of before in maybe chemistry, is the amount of time it takes for half of it to decay, which is also the amount of time it takes for there to be half of it left, right? So a colony of bacteria is growing according to the law of uninhibited growth, which means that we're not considering the fact that eventually they're going to run out of food and space. So we're just pretending they can grow exponentially forever. And T is measured in days. So the initial number of bacteria present, 150. It's just the number next to E. The growth rate of the bacteria, 0.036. It's just the number next to T. What is the population after 7 days? And T is measured in days. So 150 times E to the power of 0.036 times 7, I think it said 7 days. 193, we don't want to give a partial bacteria, so we should round to the next nearest whole number, so 193. How long will it take for the population to reach 200? So this one is harder. We need to do some work before we can put it in the calculator. So we want to know before it's 200. So 200 equals 150 e to the 0.036 t. I need to isolate the exponential expression before I can solve anything. So 4/3 need to take a natural log to get that t out of the exponent. So that's now just 0.036t because the natural log and the e cancel each other. So dividing by 0.036, oops. I'm writing all kinds of crazy stuff. Okay. So natural log 4/3 divided by 0.036. I have to make sure to get out of that parentheses or it'll take the log of that part as well. So 8 days, because remember that we're in days right now. So 8 days. How long will it take the population to double? So I could double this. I could write 300 equals 150 times blah. Or I can say, if it's going to double, then I know that after I divide by the initial, I'm going to end up with 2 equals e to the 0.036t. So I have this. So I could have actually skipped writing this down, because double is going to mean there's a 2 on that side. Okay, so natural log 2. So natural log 2 19 days to double. Okay, so the half-life of carbon-14 is 5,715 years. That means after 5,715 years, half of whatever it was is left. So we want to find K and then write the equation. Okay? So we have this. You've heard of carbon dating. This is how this is done. Now there is actually, you may have been given a formula that you just plug half-life into. And here's the reason. So we want to end up with half of whatever we started with. After 5,715 years. So these can just cancel out. So I've got 1/2 equals. And then when I take the log on both sides, I just divide by this. Right, which is the half-life. But natural log of 1/2, so this is just a note, is natural log of 2 to the -1 is negative natural log 2. So the formula you've seen is where you do the natural log 2 divided by the half-life. If you've seen the formula, then that's what you've seen. So this is the rate of decay, which means when I put it back in the formula, I'm going to actually need it to be negative . So negative 0.000121. So this means the formula is going to be a sub 0 times e to the negative 0.00121 t. Am I missing a 0 there? Yes. 0. Okay, so this is the formula. Now for this last thing, we want to solve this. Skeletons were found at a construction site in 1989. The skeletons contained 88% of the expected amount of carbon-14 in a living person. So that means 12% had decayed. So we want to know, how old were the skeletons? So here's the thing, that we are left with 88% of what they should have started with. Okay, so again, we can cancel this. We've been left with, if we know a percentage or a multiplier, we can just put that value over there. So natural log 0.88 is natural log e to the negative 0.000121t equals 0.000121t. Oh, I forgot the negative. So if I'd put the negative, this would be positive. So 1,056 and a half years it's been. And if you think, well, gosh, there's a lot of them left after that, to get down to 50%, it would take almost 6,000 years. So getting down to 88% in 1,000 years is, pretty reasonable. Okay, so this concludes my reminder video, refresher. So hopefully this helps, and I'll see you next time.